Hey everybody, first notes of the new semester. Let's do this. Okay, so everything's about electricity for about, 1.5 quarters. We've got a lot to go. So we're gonna start with static electricity, not something we get a lot of in Florida. So the word static itself, okay, refers to being at rest. Static electricity refers to charges at rest, okay? Charged objects, mostly we're just talking about electrons. And in static electricity, when we get these shocks, or we have lightning, or you have any kind of static, it's because of a buildup of charge. And it is based on the atom. We did a review on the atom, so let's talk about the forces in the atom. In the nucleus, protons and neutrons, that force is considered very strong. Let's put a very on there. Very strong. The electrostatic force, meaning the force between protons and neutrons, because, sorry, they're not going to happen, but between protons and electrons, it's considered pretty weak. That's part of the reason that when you slide down a plastic slide and you get static on you, those electrons break free. And yes, there's gravity in there. It's very weak. But it's there. So the transfer of the charge from one place to another involves breaking this force, the electrostatic force. You and I, we're not breaking nuclear forces. You need nuclear reactions. You need things like happening on the sun, okay? The transfer is only going to be electrons, never, never, never protons. Now make sure we understand the difference between a proton, which is a charged positive particle in an atom, versus a charged particle that might be positive. For example, in chemistry, remember sodium and chlorine, right? Sodium and chlorine make salt. When they break up, you get ions, okay? Chlorine is negative, sodium is positive. That's an ion. That's a charged particle. It's not a proton. Yes, it has one more proton than it does electrons, which is why it's like that. That comes into, next, electron affinity. Now that depends on the certain types of materials. That's really a chemistry thing, but I want to mention it. Certain things will not allow its electrons to be given up or broken off easily. It comes down to the chemical structure. So how does this charging, how do things become charged up? My favorite F word, you know it as friction. It could be rubbing, it could be pulling, it could be scraping. You slide your blue jean butt out of a car on a vinyl seat and you get a shock on the door handle, friction. All right, so what is charges? So back in chemistry, everything was positive or negative. What we didn't realize, what you didn't realize, is there's a number that goes with these. So first of all, protons and electrons also get referred to as elementary charge because they're the basic particles that we know of. We're not going to get into subatomic and all that. They have the same value of their charge, opposite sign. So proton is positive 1.6 times 10 to the negative 19th C for coulombs. Electrons have the same charge but negative 1.6 10 to the negative 19 coulombs. That number is going to get in your brain. What about a neutron? Well, they're neutral. They're free. Oops, I was going to write free. There's no charge. C stands for coulomb. It says how it's spelled, okay? And is considered a unit of charge. So now we have a numerical value that goes with charging. So how do we figure out how many charges are in certain amounts of electrons, etc.? So let's try these. So we're going to set up a ratio. How many electrons are in this much charge? Just to give you an idea, though, of what a lot of charge is. Think about a lightning strike. A lightning strike would be around 5 to 25 coulombs of charge based on some readings. So that's a lot of charge. So when I casually say 1 coulomb of charge, that's really a humongous amount of charge. Typically they're in sizes like this. So we're going to set up a ratio. We know that 1 electron is 1.6 times 10 to the negative 19th coulombs. Now, I'm not using negatives in here because I'm just looking for a value. And then we have x electrons, which is what I'm looking for, is in 8 times 10 to the negative 16th. Well, I don't really need to put the units in here. So the easiest way to do this is cross multiply. This times this is just going to be 8 times 10 to the negative 16th equals 1.6 times 10 to the negative 19th times x. Let's just grab a calculator and make sure you're typing these in correctly. So let's turn it on. I guess that would be helpful. So I'm going to divide both sides by this. So I'm going to take 8 second EE, back it up, negative 16. So make sure you're using scientific notation, divided by 1.6 second EE, negative 19. All right, equals 5,000. And I just use E for electrons. It could actually be E for elementary charge as well. Here's an interesting thing. One thing we know is that electrons don't occur in halves. So if I had worked this out and I had gotten 5,000.1, I have to round this to a whole number, okay? So anytime you're calculating or determining how many electrons, protons, or charges, okay, it needs to be rounded to a whole number. I literally just finished your test, and one of the last questions on it is about how many charges. It has to be a whole number. All right, the second or reverse way we could do this is how much charge do 25 electrons have? So we start with the same ratio. 1 electron is 1.6 times 10 to the negative 19th coulombs. And we want to know 25 electrons is x. So we're going to do the same kind of thing. We're going to multiply. 1 times x is x, and then 25 times 1.6 times 10 to the negative 19th. So let's just see. So these will typically come out into a little bit of the glare off of there. So what do we have? 25 times 1.6. Remember, make sure you're not using carats. You use just scientific notation key. And we get 4 times 10 to the negative 18th coulombs. All right, so that's a quick way to do that. So when we talk about charge, certain materials will hold the charge to be static and certain materials will not. A conductor will allow charge to move, okay? So we will say electrons move easily, it's an I, okay? But on an insulator, electrons do not move easily. Conductors have what we call free electrons. These are electrons that are easily moved, many free electrons. Where insulators, part of their chemical property is they do not many free electrons. Some examples, okay, for conductors, we're always going to talk about metals and electrolytes. Salt water, Gatorade, swimming pool water, they all have electrolytes. That's why you should get out of the pool when there's lightning. Insulators, silk, let me make this line a little longer. Wool, those are some fabric ones. Glass, plastic, wood. All things that can hold charge or don't allow it to move. Tape. We used plastic tape. That was an example of an insulator. All right, let's go to the next page. All right, so charge dissipation. This is the natural process where the charge wants to neutralize itself. So if something is very positively charged, it will want to take in electrons to neutralize. If it is negatively charged, has extra electrons, and it will dissipate them into the atmosphere. Moisture is definitely one of the things that dissipates and helps carry away electricity or static charge, and that's why in Florida we don't get a lot of static. All right, do protons move? Absolutely not. In the atom, they're in the nucleus, super strong nuclear forces. we have our basic rules: opposites attract and like repel, but also, let's remember, neutrals attract to charged objects. So we're going to do some pictures here, and we're going to use some numbers to represent charges. So we're going to make numbers simple. I'm going to use 4. Think of it as a charged object. It has 4 protons and 4 electrons. That's neutral. If I want to show something positive, I have to show more plus charges. So I'm going to use 4 pluses, 2 minuses. In something that's considered a negative charge, I'm going to use 4 pluses and 6 minuses. So it's based on how many. This charge is 0. This would be a positive 2. This would be a negative 2. Now, to show you that they can be charged and still look a little bit different, keeping in mind that the protons never move, I'm going to just put those in because they will never, ever, 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 ever move unless you have a nuclear reaction, which, oops, that's a plus. So here's the thing. This column is neutral. I could have all of the negatives on this side, and it's still 4 and 4. It's still neutral. I can have all 4 negatives on this side. Okay, this is now considered neutral, but now it's called a dipole, because if I were to kind of slice it in half, one side is negative, one side's positive. One side's positive, one side's negative. So they're technically dipoles, still neutral. In this case, I could have the negatives on the left also, and I could have the negatives on the right. It's a little bit stronger dipole, but overall the charge is still positive based on the numbers. And then lastly, over here, I could have 1, 2, 3, 4, 5, 6 of them. 1, 2, 3, 4, 6. It creates a dipole when they move, but the overall charge here, because it's 6 and 4, is still negative. Doesn't matter where they go, just how many. All right, that's the end of this one, and we're going to be moving on to some more things. Have a good day.